In this chapter we will talk about measurement standards, scalar and vector quantities that is used to describe physical phenomenon, and methods to determine sum of vectors. We experience the world in a form of standard of measurements. We constantly measure things such as age, temperature, distances, price of gold, price of rice and many other things. Measurement is a way of determining the value of things and how are they related to other quantities by doing conversions. In physics we also do measurement by quantifying physical quantities such as forces, length of things, time, and other physical quantities that are related to physical phenomena. There are three major measurement systems that are known, and they are the International System of Units, which is typically used in physics. In this system, the physical quantities are measured in terms of meters, kilograms, and liters. The other two systems, which is closely identical, are the British or the Imperial System and the US system. In these type of systems, quantities are measured in feet, inches, and pounds. Comparing globally the use of international system versus the imperial system, we see that majority of the world uses metric system or international system. In the Philippines, the data shows that we use metric or international system, but we actually use both, but mostly metric. Here we have some physical quantities and their corresponding SI units. I guess we are familiar with most of these quantities and use some of them on the daily basis, such as the units meter and kilograms, which we typically use when we buy things at store. Some of the quantities here are not so familiar, such as the unit for luminosity, which is candela. In later modules you will get to learn more about other physical quantities. Since the quantities are universal, then we can simply convert one to the other. Here we see the conversion from the US standard measurement or the imperial system to the metric measurement or the international system. Over the course in physics you will know several types of physical quantities and their corresponding units. Scalars and vectors are quite easy to differentiate, simply because vectors contain both magnitude and direction. Typically we encounter these quantities in our daily life, such as the physical quantity time and mass. If we examine time, it is intuitive to call it scalar because time is the same regardless of position. An example of vector quantity in our daily life is when we give direction of a location, where we give the distance and direction of that place. This is done by providing the how far it is from a position as the magnitude and informing them the name of the street or the closest structure near it as the relative direction. Shown on the table are some examples of both vector and scalar quantities. As you can see, vectors and scalars are written differently as a symbol. The scalar quantities are simply represented as basic letters or symbols, while vector quantities has this arrow symbol on top, and sometimes we call this a bar. So, for example, we call the displacement symbol as S bar. In physics, vectors are typically represented as an arrow. Drawing it this way is convenient graphically, since both magnitude and direction can be drawn easily. Shown in the figure, the length of the arrow represents the magnitude, such as shown where a vector or a bar has 2 units. The length of the arrow is a sum of 2 units. For the direction, the relative position is represented by the angle, for this case it is the angle theta, of the arrow with respect to a position such as the positive x-axis. Components of a vector. A vector lying on a 2-dimensional plane or even 3-dimensional plane can be represented by its component. For the figure shown, a vector A lies on the first quadrant in the Cartesian coordinate system at a position theta with respect to the positive x-axis. We see that vector A can be represented by its components along the x and y coordinate, with vectors ax which lies in the x-axis and ay which lies in the y-axis. Mathematically we see that vector A bar is the sum of ax bar plus ay bar. If we want to obtain mathematically the magnitude and direction, we use the equations. For the magnitude, it is the square root of the sum of the squares of its components. For the direction, it is the inverse tangent of the absolute fraction of the components. For this case of theta, the numerator will be ay since it is positioned at the opposite side of theta. The denominator will be ax since it is positioned at the base of theta. This method of obtaining the magnitude is also called the Pythagorean theorem in mathematics. Vector components is used as a mathematical method in determining addition of several vectors, and this method is also known as component method. Another concept we need to know is the idea of unit vectors. Unit vectors are simply the fundamental units that a vector can have. This would be one unit. So unit vectors are represented by the symbols I hat for the x-axis, j hat for the y-axis and k hat for the z-axis in the three-dimensional coordinate system. The symbol hat represent that the symbol is a vector quantity but the basic unit of that vector. For the figure shown, a vector is lying on a two-dimensional plane with the unit vectors as I and j hat. Mathematically, we rewrite the component of vector A as an expression in terms of its unit vectors. We see the separation of the magnitude given by the ax and ay and its components I and j hat as the direction. Let's say we have three vectors and we are asked to determine the sum of these vectors. So, we have three vectors A, B, and C with their corresponding magnitude and direction. First step is to break down the problem. We identified three directions based on the problem which we will assign vectors A, B and C. We then break down these vectors into its components. Second step is to break down each vectors into its components. Vector A lies on the first quadrant in the Cartesian coordinate system and that suggests that it's on the positive x and y axis. So, for vector A we have the component for its x-axis as the vector A times the cosine of its angle alpha equals to 37 degrees. AX here yields a value of about 79 newtons I hat. For its y-axis its AY is a sine function of the angle alpha which yields a value of about 60 newtons J hat. So for B we see that it is positioned at the second quadrant. This suggests that the x component is a negative value and the y component is a positive value. Here the value of beta is measured from the negative x-axis. Beta is measured by summing the angles of two quadrants which is 180 degrees minus the angle 150 degrees and obtain the value of the angle as 30 degrees. This is with respect to the negative x-axis. Similar to what we did with vector A, the bx component is a cosine function of the angle beta but we multiply it by a negative I hat and this is because it is on the negative x-axis. The value of bx yields to about negative 86 newtons I hat. For the by component, it is a sine function of the angle beta and it is a positive j hat since it lies on the positive y-axis. The by component vector yields a value of 50 newtons j hat. So for C, it is positioned at the third quadrant. This suggests that the x and y components are negative values. Here the value of gamma is measured from the negative x-axis. Gamma is measured by summing the angles of three quadrants which is 270 degrees minus the angle 233 degrees and obtain the value of the angle as 53 degrees. This is with respect to the negative x-axis. Similar to what we did with vector A and B, the cx component is a cosine function of the angle gamma but we multiply it by a negative I hat and this is because it is on the negative x-axis. The value of cx yields to about negative 48 newtons I hat. For the cy component, it is a sine function of the angle gamma and it is a negative j hat since it lies on the negative y-axis. The cy component vector yields a value of negative 63 newtons j hat. The third step for the mathematical method is simply summing all the x and y components of each vectors. Here we simply sum the component vectors that lies along the x-axis. We get that the resultant vector's component along x which is approximately equal to negative 54.89 newtons I hat. Similarly, for the y component of the resultant it is around 46.29 newtons j hat. Here we use the components of the resultant to visualize the location of the resultant vector. We see that it is positioned at the second quadrant. We can use the negative x-axis as the relative point for its position. To measure the magnitude of the resultant vector we can use the Pythagorean theorem we learned earlier. Also, to measure the position theta we can use tangent function where ry is on the opposite side of the angle theta and rx as the adjacent side of the angle theta. To determine the magnitude of the resultant r we use the sum of the squares of its components. Substituting the values of the components onto the equation we get the values for the resultant as positive and negative 71.80 newtons. However, we simply use 71.80 newtons because we are only measuring the magnitude of the resultant vector. For the position, we use the inverse tangent function where the numerator corresponds to ry and the denominator as rx. The choice of numerator and denominator depends on which is on the opposite and adjacent side of the angle being measured, and for this case Ry is on the opposite side and Rx is on the adjacent side. Substituting the components we get 40.14 degrees with respect to the negative x-axis. Do not forget to write clearly your solution and box your final answer. Adding two or more vectors graphically. Polygon or tail-to-tip method and parallelogram method are graphical methods of adding vectors. Let's give an example for polygon or tail-to-tip method. Let's say, an explorer in the dense jungles of Africa leaves his hut. He takes 40 steps northeast, then 80 steps 60 degrees north of west, then 50 steps due south. Find the displacement that will return him to his hut. First step is to break down the problem. We identified three directions based on the problem which we will assign vectors A, B and C. Vector A has a magnitude of 40 steps and the direction is northeast. To say northeast simply means the angle is 45 degrees, and this is also true for orientations such as southeast or southwest. The second vector B has a magnitude of 80 steps 60 degrees north of west. So the angle is measured from west going to north. The last one is vector C, which has a magnitude of 50 steps going south. Let us draw this using polygon or tail-to-tip method. We draw first vector A, which has a magnitude of 40 steps and the direction is northeast. This suggests that the angle relative to a position is 45 degrees. Then we draw the second vector B, has a magnitude of 80 steps 60 degrees north of west. So it is measured from west going to north. The last one is we draw vector C, which has a magnitude of 50 steps going south, or here it is drawn going downwards. Using polygon or tail-to-tip method, we draw an arrow where its tail intersects the tail of the first vector or vector A and its head intersects the head of the last vector or vector C for this case. This arrow is the graphical representation of the resultant vector R. However, for this problem you need to reverse the direction of the resultant to obtain the displacement needed for the explorer to return to his hut. Here we see that it is positioned between south and east. Another method is the parallelogram method, which is done by simply putting all the tails of two vectors together, then drawing parallel lines of those vectors forming a parallelogram. Then an arrow is drawn where its tail is at a position as the other two vectors and its arrowhead intersects the drawn parallel lines. Or simply draw a diagonal arrow on the parallelogram with its tail at the origin. Here we have two vectors A and B, and when add together we get the resultant vector. Comparing the two graphical methods, it seems useful to use polygon method to determine more than two vectors. The end for now. For questions and comments you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at dies@dieslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.